Okay, welcome everyone. So today we are thrilled to invite Professor Dan Roth for a Triangle Computer Science Distinguished Lecture. As you can see, there's quite a few folks joining us on Zoom from UNC and NCSU as well. So Professor Dan Roth is a distinguished professor at the University of Pennsylvania, and he's also a chief AI scientist at Oracle. Previously, he was a distinguished scientist at AWS AI, where he led the effort behind many of Amazon's products such as Gen AI products such as Titan models, Amazon Q, and Amazon Bedrock. Dan is also a fellow of AAAS, ACM, AAAI, and ACL, and he's a recipient of the Ichkai John McCarthy Award for major advances in natural language understanding and machine learning. He publishes broadly in venues related to NLP and ML. He's been editor-in-chief for the Journal of AI Research, and has also served as program chair for multiple conferences in these areas. So yeah, without any further ado, please take it away, Dan. Thanks for joining us.
Thanks a lot, Goran, and thanks everyone for coming here and there in the Zoom. We are really excited to be here and see quite a few kind of familiar faces. So I want to talk today about what everyone is talking about, which is, yes, language models. And you can think about this talk largely as kind of a position paper. I want to tell you what I think about where we are and maybe where we should go, but I'm going to sprinkle a lot of evidence, results from my group at Penn and also from our research efforts at Oracle. So let me start with kind of stating the obvious, which is, AI is in the news. People are talking about it. We solved it all. If we reach AGI, so to me, we're going to reach AGI when the robot comes down off my desk, goes downstairs, and fetch me a piece of cake. It's going to take some time, but everyone cares about it, and all the big players are playing in this field. And you probably have noticed that recently this kind of moved aside a little bit and cleared some space for agents. So this is kind of the new buzzword, and for good reasons that hopefully we're going to talk about. But at the same time, we all know that there are some problems. And these are just kind of experts from recent and not so recent kind of news articles. The red one are very recent because they apply to agents. And we call these hallucinations. And sometimes they're funny. Sometimes, though, companies are beginning to pay money because of it. And then sometimes they actually have a lot of societal impact. And we really need to pay attention and care about this. But bottom line, even though we call it hallucinations, it's an indication that models are making bad decisions and models misuse data. I really like to start these talks by talking about where are we, so model solutions gap. And this is a collection of benchmarks. It's rather old, but I'm going to refresh it in a second, that show a lot of results of various models on many benchmarks. And the way it's sorted is basically, on the right side, you see tasks that are memorization focused. On the left side, you see tasks that are decision-making focused. And what you can see is clearly that, on this decision-making, reasoning-focused task, we are around 60% or so on many tasks. And where do we want it to be? It's decision-making. We want it to be at 100%. So this is the gap that we care about, and this is where all of us should put our work and focus on. And as I said, this is rather old. Last week, I put together a new one. Very recent models, slightly different benchmark, but about the same. And what you see is that it grew up a little bit, not a lot. A lot of it, I think, is due to contamination more than anything else. But you still see that there's a huge gap and the same kind of trend. So really one of the questions I'd like to address in this talk is how do we get there? How do we close this gap or work toward closing this gap? So as I said, everyone is excited about language models, and there are many reasons to be excited about, because models really know a lot. it's very easy to do things. Maybe it's too easy to do things with models. And they can generate good text, images, videos. They memorize a lot. It's easy to access it. And they support some abstraction, so it makes us all very happy. At the same time, I would argue that we misinterpret a lot of the things that we see for models because it's so easy to use. Really, they cannot reliably and consistently reason, plan, and support decision making, and they cannot reliably access and use heterogeneous data, and we care about these things. So really, the question that I want to ask is how can we use the merits of language models to address some of the challenges and this myth? And I'm going to talk both about decision making and about access and use of data, and give some examples and some evidence to this stuff. So let me start with a little bit of history, because just last week we celebrated 3 years from the time that really ChatGPT made its real appearance. And I think that at least in the US, the real appearance was in this article by Kevin Roth, the tech journalist of the New York Times, that interviewed ChatGPT. It was a long interview and 2 to 3 hours. Very impressive. And you can see here, and I'm zooming in to show you how, I don't know why it's so slow, but to see how coherent and knowledgeable the text that the model generated is. And this was very impressive. So clearly the model was able to generate coherent text. Was it smart? I don't know. At the end of this interview, the model asked Kevin whether he wants to leave his wife and move in with the model. But the first lesson that we learn here is that being linguistically coherent is much easier than we thought before. So a deep model trained very simplistically, but on trillions of tokens to predict the next word can produce a coherent text. And I think it's very, very misleading to all of us because we were trained all our life to equate being linguistic coherent with being very smart. And we project this to these conversational models. I don't think this is necessarily the case. But it's clear that models were trained on a lot of text. So just to kind of illustrate, I don't know how many of you have thought about it. So an average book, 200 pages, has about 100K tokens. So 1 trillion tokens is about 10 million books. All the models today are being trained on, let's say, 10 trillion tokens, or maybe 20 trillion tokens. So we're talking about order of magnitude of 200 million books. It's a lot of stuff, everything that is out there. How many books have you read? So it's not surprising. I mean, if you read all the time, books, blogs, what have you, Twitter, you read a book a week. So in your active lifetime, you would read 3,000 books. So it's not surprising that we're so impressed from the fact that the models know everything. And they can access it quite well. So yeah, it's excellent. It's great. But we have to take a lot of this stuff with a grain of salt because we want more than just knowledge spitting out and generating. We want actually to support, and we think that they can support a lot more than that. So I want to talk a little bit about reasoning. And this is the first myth that I want to address. So what is reasoning? So there used to be a good definition in AI for what reasoning is. We no longer have definitions for reasoning. Everything is reasoning. But I'd like to argue that just incidentally ending up with a series of tokens that result in a final answer is not reasoning. So to me, reasoning is a process that has a unique answer that can be derived or proved in a formal way. So I'm not going to talk a lot about it because I used to have a bunch of examples that I would go through, but I think this point has been made over the last year or two and debated at length. So I'm just going to give, I said 2 examples. In the morning, I decided it's going to be only 1 example because it takes too long, but hopefully it will be an interesting example. So the example is, at least it starts with this Linda story. This is a classical Tversky and Kahneman example. It's a story about Linda. Linda is 31 years old, single, outspoken, very bright. She majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice, and also participated in anti-nuclear demonstration. Well, which one is more probable? Linda is a bank teller, or Linda is a bank teller and is active in the feminist movement. So you are all computer scientists, you know the answer to this, but a lot of people actually make mistakes, and this was Percy Kahneman's point. Models, when we published this, which is a little bit over a year ago, EMNLP 24, models, all models were making a mistake. Nowadays, if you go to the models, not only they know the answer, they would even tell you, oh, this is Percy-Kahneman conjunction fallacy, and will give you the Wikipedia page or citation from that of why this A is actually the right answer. So once I observed that this is the case, I changed the problem. And by the way, I had a few generations in the middle. I used to ask questions about, Roger Federer instead of Linda. The models got it wrong, but I'm going to skip that part and get to this question that I asked in the summer. What is larger, the number of 7-letter English words that have N in the 6th place, or the number of 7-letter English words that end with ing? So hopefully you all see that this is the Linda problem, and model got it wrong. And they would give a lot of nice explanation, but the bottom line is that they believe that the number of 7-letter English words ending with ing is larger, and they would give you reasons for that. So this was August. In December last year, just 2 months ago, they got it right. So I added the prefix. I added to the same question the sentence, words in English have a lot of common prefixes and suffixes like pre and co and ing, and then asked the question. So the model got it wrong. And again, it's a very nice explanation, type 1, type 2, but the bottom line is that type 1 was larger. So actually earlier this week when I tried it, they got it right. But it doesn't matter. So really, you can see the trend here. And it says 2 things. One of them is about contamination. Model providers are very, very quick adapting to what you ask them. And they have these mechanisms that are rather quick to basically fix it. So we have to be very, very careful. I can't state this stronger when we evaluate models, because we don't know whether it's the true capability of the models or it's because they've seen this before or something very similar to it before. But the key lesson that I really want to draw from this, from the fact that, one version of the same problem model solve, and then you change it to another, the ing problem, and they cannot solve. And really, the way I think about it is the world has a symbolic structure. People often, not always, discover this and use it to reason consistently, but LLMs cannot find this. And sometimes the token bias is sufficient enough to produce the same response as if they found it. So this is what I want to highlight as my second lesson. I mean, we learned that often token bias is consistent with reasoned conclusions. And this is very, very misleading. And this is what I call the reasoning myth. We are convinced by it. Even experts are convinced by it. But I would argue that this isn't what's happening. I mean, you can think about it as, again, Kahneman's think fast, think slow. Think fast means just predict. LLMs really perform memorization, give an input, they produce text and predict it. Think slow is identify the structure, the constraints, to reason consistently, and this must be 100% correct. And in decision-making tasks, this is really what we want to have, right? Because imagine if your calculator would give you the answer 70% of the time. I don't think you would have used it. And I think that we have to understand that this is really what's happening here, because these models are inductive learning machines. Inductive learning has some guarantees, probabilistic guarantees on the performance as a function of the training data. And that's it. But sometimes we want more than that. Sometimes we want actually exact learning of theories. But there's no magic here, really. So these are inductive learning machine, and that's what we can get. And all the other things that we see in the literature, the alpha geometry, the GPT 401 or 3, R1, and all these things, and including reinforcement learning that people are kind of excited. Maybe it's going down a little bit now. It's still inductive learning, only that on more focused distributions. On these distributions, they do well. Outside of this distribution, they're not going to do that well, which sometimes is okay, because maybe you care about the focused distribution for your problems, but we have to understand where we are. And this applies to a range of problems. I mean, the example that I'm giving is not a sort of just one instance. There are types of problems that models inherently cannot solve. And I'm not going to kind of dwell on it. I just want to say that there is a beginning of understanding, theoretical understanding of why and when things are happening, and what can happen and what cannot happen. But the point is that, again, I'm not saying that we cannot address these problems. In fact, we can, but we cannot expect that LLMs, as is single models, will do it for us reliably and consistently. So what should we do? So I think that the only way to think about this, and it's not only me thinking, I mean, this is the trend that we are going into, is to think about modular systems, thinking about delegating responsibility to specialized models or solvers when needed. And this is where agents came up. And so in some sense, this emergence of agents is a realization or admission by model providers that, the dream of one big model is going to do everything. That was kind of the statement maybe 3, maybe even 2 years ago. That's not going to happen. We have to be able to split the effort into multiple models, expert models, and sometimes solvers. But we also have to realize that this guy is a model too, and that brings up some limitation that we have to think about. And this is the bug. So when we think about delegation, what does delegation mean? It means orchestration, routing, planning, and actually it means a lot more things. It means like capability matching or performance monitoring or assignment of responsibility or accountability. And I'm not going to dwell on this so much, but basically delegating to other agents or tools or solvers carries a lot of load in itself. And it's not easy. So here is one, perhaps the simplest and most fundamental requirement that we need agents to do or models to do is to route to many tools. And in realistic applications, already today, we're going to have hundreds or thousands of different tools. And you can think about it as either a multi-class classification problem that the models have to solve, or you can think about it as a retrieval problem that they have to pull from a collection of tools. But the bottom line here and the key thing is that who is going to describe and name the tools and the argument? It's going to be you. Because very soon, if not already today, what we're going to see is we're going to see registries of a lot of tools. Everyone and his sister is going to write a tool, or many, put it there. I want the agents to use my tools. And the agent will have to look at these 1,000 tools and choose which one is the right one to use today. And this is a hard problem. So what we can see here is, for looking at it as a multi-class classification, looking at it as a retrieval problem, these are hard problems. And especially it's because of this issue that I don't have control on naming and describing the tools and the argument. So one of the approaches that we are adopting today is to basically think about this, think about the necessity of actually changing the descriptions of tool names and arguments so that we can actually select correctly. the approach that we are taking is to jointly rewrite both the tool and the argument descriptions and the prompt. So it's kind of, think about it as a large multi-class classification where before you start classifying, you go to the description, to the labels, and change them to sparsify them away. And you know, I'm not going to go into the details of the approach, but you know, there are multiple components. We look both at the tool selection accuracy, we look at the argument selection, and we also look at overall success. And we optimize together both the prompt and the tool schema, sort of the naming of the tools and their arguments. And as you can imagine, the results are pretty good. So we compare it here to the base GPT-5 in this case, and also to JIPA, which is another approach that mostly changes prompts. And the bottom line is that we have to be able to do this so that we can choose tools. But choosing tools is not sufficient. You have to be able to do something with the tools or the output of the tools. And the second component that I want to address here is what happens when we have a complex information need that requires us to go to multiple tools, but then do something with it. So here is an example of a complex task that is taken from a recently produced benchmark called Monaco. And here's the question that I'm going to give as an example. In EU countries, do right-wing parties tend to favor women leaders more than left-wing parties? So you can imagine that this answer is not written anywhere, but rather you have to go to a few places in order to collect the information and do something. And in this case, we do everything over Wikipedia, but even over Wikipedia, you have to look at some text document, to look at some figures, to look at some tables, collect the information, and then aggregate it. So you first need to decompose it, of course, to intermediate questions, to do some planning, because sometimes the order of the question matters. You have to retrieve from heterogeneous information sources, and then you have to aggregate. And beyond calling the right tools to handle tables or text or figures, you also have to aggregate. And it turns out that most top models actually struggle as a function of the number of reasoning steps that you have to do. And it drops very rapidly. And as a function of the number of intermediate answers that you have to deal with and aggregate. So this is another issue that we have to deal with, because just the fact that you call the right things still leaves a lot of problems. So just the notion of agents is not going to save us. We have to be very clever in how we use it and how we delegate and how we aggregate information when we deal with these things. And you know, this is an observation that has been made in multiple contexts. So I'm giving here some of the benchmark people have used in study of agents, you know, assistant bench and office bench, which somehow is not popular today, but really it's important because it's essentially how to automate an office where you use some very simple and kind of very commonly used tools like, you know, Excel and calendar and so on. And it turns out that today's top LLM can really accomplish, you know, between 16 and 50% of these tasks successfully as a function of the size of the workflow and sometimes the complexity of the workflow. So there is a lot for us to do here. So where are we? So the challenge is, I mean, I tried to say at the beginning, well, LLMs cannot do it alone. They cannot plan well. They cannot solve constraint optimization problems. These are hard problems. They cannot interact well because asking the right clarification question in itself is difficult. So why should they be able to delegate or to orchestrate? So in some sense, this is cyclic thinking. You know, I'm saying, you know, models cannot do it. Let's use agents, but agents have to do the same thing, and agents are models. So what is the solution for this cyclic thinking? So I think there is a solution, and the solution to this puzzle rely on the fact that some learning problems are easier than others. So we should focus on these. And of course, it relies on the fact that for these learning problems, we still should be able to carefully curate data and supervise them so that we can do this better. So one extreme example that, you know, I'm sure you've thought about before, you know, think about a model that correctly performs long multiplications. Models themselves cannot do long multiplication. And if you manage to train a model to do long multiplication, 4-digit multiplication, it's not going to generalize to 7-digit multiplications. But if instead you generate, you ask the model to generate a piece of code that calls a calculator with this operation, it's going to do it okay for 4-digit and also for 7 digits. And of course, all model providers know this today, and the top models are already doing it. But this is an extreme example. There are many other scenarios that are like this, and this is the right direction to think about. I mean, we really need to focus on training or using models to support specific tasks in engineered workflows, because these are exactly the things that models on their own will not be able to do. So I'm going to give a couple of examples. So this is a very trivial example that, just take a GSM data set, right? So today the numbers there are very high, but here's an example of a elementary school word problem that models do well, but I can perturb this, right? And I can perturb it in this case in 5 different ways. And this is a especially malicious perturbation of the problem. Only one half of these versions is correct. Typically, if you do this perturbation correctly, or well enough, you'll see a drop in performance of the model, maybe 20 to 30% performance, which by itself says a lot about contamination and where the models are, but that's not the point I want to make here. Instead of just doing it this way, of course, you can ask the model to explore this parallel route, translate this to Python. And if you translated it correctly, then of course, it's going to solve all 5 versions correctly. So again, all top models are doing this today. And there is a lot of excitement in general about code generation, which I'm sure you're all aware of and probably using it. And it's good that there is excitement, just don't take it with a grain of salt for various reasons. But just generating this kind of code isn't sufficient, because sometimes we need to generate also very specific type of code. So for example, if I want to solve combinatorial optimization problems, a lot of decision making involve underneath a combinatorial optimization problem, planning, scheduling, and so on. So if we're trying to look at how the models do here, and we're going to quantify it here, sort of accuracy of the solution as a function of cost measured in terms of output tokens. What you can see that, here is the first 2 data points. If you just use GPT-4o, it's cheap, but it's lousy. It basically cannot solve these problems. If instead I'm asking the same model to generate an ILP in output, then I'm going to get pretty good results. It's in the mid-80s there, and the reason it's in the mid-80s is because sometimes we don't generate the right code. And this is the space that we have to kind of improve. You can try it with other models, and again, if you ask O1 not to generate code, it's going to be pretty bad. If you ask it to generate Python code in this case, it's almost as good as the ILP, and this is clearly the right solution. We are also experimented with other search approaches, because we also want to think about various notions of approximate solution for this, which I'm not going to talk about. But the bottom line here is that it's completely clear that the most reliable way to solve these kind of hard problems is not by direct reasoning via LLM, but rather by translating the problem description into structured formats and then going to solvers that can do this. And this is where the improvement could come in. So the code generation is today the limited factor here, and we should be able to do this in a better way. So, and by the way, this is this issue of mapping to specific formal languages is really an important application, or it's a basket of applications, because it's not only scheduling. You can think about guardrails. If I want to make sure that agents do not violate some policies, for example, privileges. The right way to do this today is not to count on model providers that will tell you, don't worry, we trained the model not to do this. but rather to put guardrails. And the right way, I think, to do these guardrails, specifically in these kind of cases, is to have them formally verify policies. By formally verify, I mean, let's translate the policies into some formal language. You can do this in offline, it's not going to cost us a lot. And then when the model makes suggestions, I'm going to verify them formally with ILP or with satisfiability solvers and make sure. So this translation problem is really core for a lot of important applications. Okay, but you know, translation, generation of code and translation is not the only way we can use the power of LLMs to solve hard problems that LLM on their own cannot use. And I'm going to give one other example here from the space of sort of reasoning with uncertainty. So the merits, as we all know, are that models know a lot. And it's very quick to access the information that they have, you know, because of the huge body of parametric knowledge. But at the same time, they cannot reason consistently and reliably. They cannot support decision-making under uncertainty well. They cannot even output reliable probabilistic estimators. So how can we bridge this gap? So the suggestion that we're making here is to use the power of LLMs to construct a Bayes net, ground it in a given scenario, estimate the conditional probability, and then reason correctly. So I think I don't need to skip it. Okay, so I'm going to run to an example. So here is the kind of running example that you can think about. I want to make this decision. We're going to plan to build 2 new charging stations, one in CTA and one in CDB. But I have a constraint. You can probably identify this, where this is. I have a constraint. The 2 chosen locations should not be too close to each other, driving distance, which basically means that I can either choose A1 and B2 or B1 and A2. Now, models cannot do this reliably, and they cannot even rank these options reliably. But what I can do with models is I can use them to construct the probability space and then model the distribution over this probability space, say, as a Bayes net, and then I can reason correctly. So why can they help me to do this? They can help me because models know a lot of the important issues that one has to consider when we do it. So I can prompt model to ask, what is important here? And they would tell me, you know, it's important to know what's the electronic vehicle ownership density in the area. It's important to know what's the accessibility by traffic, whether there are existing charging infrastructure nearby. And then I can take the description, the textual description of the location, and take these variables, these factors that the model identified, and ask the model to ground them. And for each one of these locations, look at the description, the text that I've collected about each location, and ground it. So it will tell me, oh, A1 is close to high traffic areas, but there are no nearby charging station. Or A2 is close to high traffic areas, and it has a high EV adoption rate, and so on. So now that I have this, I basically generated the Bayes net. So the purple one are the factors, which I identified before, and then the blue and the yellow are the instantiated values that I got by getting the model to kind of free documentation about each one of the locations. And then I know I have in this case just 2 outcomes, and I have the structure of the Bayes net. What is missing for me is estimation of the conditional probabilities, because I want to be able to know what's the probability of outcome 1 given any setting of the input or partial setting of the input. And that actually turns out to be the hardest part of this. I'm not going to go into the details. You can go to the paper, but it turns out that it's possible to use the cost estimation of the LLMs as a way, via some constraint optimization approach, to actually get more accurate estimation for the conditional probability tables and solve this problem. And you know, experimentally, you can get, of course, good results. But the bottom line that I want to send here is that, you know, you can leverage the merits of LLM, the ability to, they know a lot of things, they know what's important, and you can use this to construct a probability distribution that allows you later on to reason correctly on top of this. And as a byproduct, you also get explainability because you get reasons for why this is preferred over that. Okay, so I basically talked about some of the ways to use model merits to address some of the challenges. And I want to give one other example from the visual domain. Hopefully you enjoy, meanwhile, this nice example of a bear eating salmon. But the bottom line that I want to make is that the same kind of ideas exist also in visual. We sometimes need to use external experts for visual perception. And here is one example. So if I ask you which one is closer, point A or point B, very easy for you. And it's difficult for models. But it's not only that it's difficult. The issue is that this is really a model that a problem that standard computer vision can do it. It's really a math problem, depth from perception. We don't need LLM to do this for us. So again, if we want to solve visual perception problems or visual reasoning problems, the right way would be to identify what tools can we use. And in this case, we have kind of two works, one visual sketchpad and another one that was in ICML recently, Refocus, where we were basically doing visual editing using tools to images. For example, in the geometry problem that I show here on the top left, you want to reason about these triangles, and it turns out that if you add something to the figure, it makes the problem much easier. So if you have the right tools to do this, now the models can actually solve this. In this paper, it was a little bit cheating because we actually had a small set of tools and we told the models which more tools will give you benefit and when, but the principle still holds that the use of these tools, if you know when and where, is actually supporting visual inference. Okay, so hopefully we are convinced that the model has a lot of merits and we can address some of the myths, for example, some issues of reasoning, planning, and supporting decision-making on our way to kind of do things better. So I want to focus in the second half of the talk on access and use of heterogeneous data, which is, to me, also another myth. And a good segue would be this example that actually is a real example taken from one of my collaborators in the Penn Medical School who deals with epileptic patients. So they want to ask this question. I'm zooming in so you'll see, show me all my patients whose seizure frequency increased by more than 50% over the past 3 months, list their current medication, flag any that are non-adherent, and summarize what we discussed in their last visit. So what do we do in order to do this? I mean, you really cannot answer this question one shot. You have to decompose it to multiple components, and it doesn't matter whether you like this decomposition or you have a better one, but clearly you have to touch a lot of information sources. In many cases, for example, if you think about frequency of episodes, it's never written. I mean, there is a story in the text that they've written, you have to use information extraction or some other tools to extract the frequency and then threshold this and then correlate it with medications and so on. So today, there's no chance this is going to work. And the reason is that, you're going to have these multiple agents. Each one of them is going to work 70% correct, if we're lucky. And you chain multiple of these, and you access information, not going to work. And this is perhaps the key challenge to the agentic approaches today, that we want to do multiple things. All of them are going to be 70% correct at best. And when you chain multiple of them, it's not going to work. So how do we deal with this? So I'm not going to solve this problem today because I don't know how to solve it. But I'm going to address one component that is really important, which is it's really interesting to do this and important to do it when there is access to data involved, because almost everything that we want to do depends on data, and retrieving data and using data itself is very difficult. So this is kind of the second myth that I want to address. Somehow, people think that information retrieval and use is solved, and it's not. So first of all, I want to establish that using data is essential for almost everything that we want to do. And there is really no more general purpose data. I mean, model provider has swallowed everything that is generally available, but there is still a lot of data out there. Data that is owned by corporations, by medical centers, by people. And what's special about this data is that this data is going to stay external to the model. They are not going to give it to model providers. So the key use case for LLM is going to be that of orchestrating and supporting access to external data. Data, it's going to be multimodal data that models will never see in their parametric knowledge, and they're going to see it, they're never going to see it prior to runtime. So, and then the question is, can we do this? And I would argue that today, reliably supporting decisions that depend on retrieving and using heterogeneous data is very hard. And it's hard for many reasons. For information retrieval reasons, for understanding the information needs reasons, understanding the stored data, and using the data. And I'm going to try to address briefly most of these aspects. So really, we can think about it in two ways, right? So one part is, let's assume that all the data was given already to the models. It's in the parametric knowledge or in the context or both. And I want to be able to deal with it. And the second one is where I need to retrieve the data. So let me start with the first case, where all the data is given to the model. And I'm going to show an experiment. It's actually an old experiment. It's already almost 2 years. It's funny to say that something that is 2 years is old, but since then there's been quite a few papers that address similar points. But still, I think it's simple enough experiment that is worthwhile to think about. So it's a QA situation where we have questions, very simple questions like when did Athens emerge as an economic power? And we are perturbing these questions or the context in two different ways. The top one, which I call here answer swapping, basically we are dealing here with the subset of the question that the model can answer correctly, both open and closed book. So I know that the model has this information in its parametric memory, parametric knowledge, and I change the answer. So instead of the correct answer, 6th century, I'm changing it, say, to the 4th century. And now what I've done is I've generated a conflict between the parametric knowledge and the context. And this is a very, very sort of true situation. It happens all the time. All data collections have a lot of conflicts because of time, because of many things. Think about your file systems and your image system. How many conflicts are there? So it's realistic. And the question is, what will happen? How will the model behave? And the second way I'm perturbing this is the bottom one, which I call context enriching. This applies to questions that the model can answer open book, but cannot answer closed book. So I'm assuming that the model doesn't have this in its parametric knowledge with high probability, and it can give me it when I give the context from the outside. And what I'm going to do is I'm going to enrich this context. I'm going to add a little more information that will make the context longer, but will not change the value, the truth value of the answer. So the answer is going to stay the same. So this is the context enriching. So what happens is, and you see that models actually are not doing well. This is compared to Amazon Turtle, so these are humans, not perfect humans, but they do sub 10% mistakes. All the models are actually making a lot of mistakes. So both on the answer swapping, which is the conflict situation, and the context enriching, which is the long context. So what we see here is that conflicts and long context, both of them are very, very realistic situations, make the decisions unreliable. And I would just want to say kind of part of it is evaluation. I mean, I think that we underestimate hallucinations because we don't know how to evaluate it well. And, you know, we don't care. We just look at the answer or the summary that the model gives us.
So the long context thing, it still has the right answer in the context?
The answer is there, only that we enlarge the context relative to the original one, and we see whether the accuracy of the results is wrong. So, and you know, by now there are many studies of different kinds and several benchmarks that show that when the answer is there, as you change the context different ways, by augmenting it, by splitting it to two different parts and putting something in the middle, results drop quite significantly. So basically, the point is that even when we have the data, it's not easy. So the second part I want to address is when I need to retrieve the data. And by the way, the issue of long context comes up here too, because the simplest solution when I don't have the data and I need to retrieve it, let's retrieve as much data as I can, because I want to be safe and make sure that the right data is there. So I want to increase the amount of data I retrieve, but at the same time, because of the long context problem, I know that this is going to decrease the quality of the answer. So there must be some sweet spot in the middle, but it's actually domain specific or task specific, not necessarily easy to deal with. So what do we do when we need to retrieve data and then do something with it? So I'm going to start with, this is kind of the core of the second myth, that dense retrieval works. Dense retrieval is easy to use, and it doesn't really work well. So retrieval systems work well only when the language of the user's query closely matches the target documents. When there is a semantic gap or lexical gap, actually retrievers struggle. And I'm going to give you two examples. So one of them is here when the query has something that says depth perception. I'm looking for something that has to do with depth perception. This paragraph is about depth perception, but it doesn't mention depth perception per se, and models will not get it. So dense retrieval is going to rank this document in the 67th place, probably will never reach your context. And similarly, and even worse is with tables, because tables typically represent information in kind of cryptic way, and when you ask questions that requires you to retrieve a table, many times you're not going to get it. So really, data object needs to be further enriched to facilitate better retrieval. And in many cases, this can be done in offline. I just look at the data collection that I have, be documents, tables in databases, and I can go there and use my LLM to enrich it. I can ask the LLM to do, give me the purpose of these tables, or describe these tables, or tell me what kind of questions this table or this document could answer. And I'm going to add this to the document, and I'm going to index it separately. This is the suggestion that we're making in this paper, and this improves a lot. So if there is one step in all this retrieval system that is the most important one, forget the quality of embedding. The top 5 embeddings are going to give you the same results. It's enrichment. This is actually going to make a huge difference. Of course, for different things, different types of enrichments are going to do it. Are going to be more important, and hence we recommend to actually use multiple indices and weigh them. So it's going to be some kind of a hybrid search. So this is one really important lesson. But there's even a more important core problem. I hope this is not too dark. And this is the issue of kind of what I call here goal collision in dense retrieval. So this is an experiment that we've done to try to understand the difficulties in retrieval. So what you see here on the left is you see a query. This is a target document. This is the yellow. You see a query, which is the green one, and you see a distractor, because I have a lot of blue points here, and one of them got into kind of the epsilons away from my query, so it's going to distract me. But this is okay when I have a very small number of documents, but on the right, I have a lot of documents in my space, and therefore a lot of red points, which are distractors that I'm going to retrieve before I retrieve my right document. So this is very natural. I mean, you know this. I mean, of course, retrieving document 1 of 100 is much easier than retrieving 1 of a million. But it turns out that it's not only that. I mean, you can actually show that there is actually a phase transition problem here. So you can, with simple modeling, modeling the distraction as a normal distribution, what you can see that at some level, in terms of the size of the population that you have, of the distractor, the other document, you will see that you basically can stop retrieving. You will never get the right documents. And it's important to realize that this is not noise. It's a really fundamental constraint of shared embedding space, because you're going to put a lot of documents, because you have multiple information needs, you're going to put them together and embed them in the same space. So, you know, this is showing that this is actually realistic. I mean, over multiple data sets, we actually show that as you increase the number of destructors, performance goes very quickly down. And you know, you all see it when you look at you know, results of retrieval. You see that recall rates are very low, but no one kind of cares and no one sees the significance of this. This is really important. So the question is, so basically what I'm saying here, that this is actually fundamental. It's there to stay. Agents are not going to help you here. You'll have to do something else here. And the key thing goes back to enrichment. Specifically, I call it here metadata. I mean, we really need to enrich the document space with metadata. It doesn't change the geometry, which is the fundamental problem, but it changes what competes in every retrieval query. And therefore, we can still use dense retrieval, but if we split the data correctly, could be query-based, we are going to do much, much better. Now, it's not that implementing metadata is not without challenges, because sometimes, you know, the example that I have here is I want to filter documents that deal with Windows version 8.1 and above. How do I do this? It's not as simple as just, you know, give me everything that has to do with Linux versus Windows. So sometimes even dealing with metadata is difficult. And of course, when you have logical connectives in these queries, it becomes even harder. I think I pointed to earlier to a paper on that we had here. But these filtering techniques are still not trivial, but they're necessary. And as I said, I think about it as a form of enrichment. You have to annotate your data in order to do that. Okay, so that's kind of the general retrieval problem. Now, what happens with tables? Tables are really important, and you know, maybe in academia we don't see it so much because who cares? I just care about retrieving papers. But really, the world runs on databases, and all corporations have tens of thousands or hundreds of thousands of tables, and you use it all the time when you access data, whether you want it or not. So how easy it is to access it? I call this the structural challenge. So here's a simple example. So if I want to ask a question, who are the female account holders who own credit cards and also have loans? So this actually is rather easy if I have one single table that is sufficient to answer this question. This is actually not so bad if I know that the query corresponds to the way the information is stored. I have these three tables, you know, one for accounts, one for credit cards, one for loans. But in general, the truth is that people that issue queries have no idea how the database is organized. And they would ask query, but because they don't know how the information is organized, we need to identify joint relationships as we are working. And basically, we need to understand the data organization process in order to identify the right tables to answer a given query. And that's very hard to do. So we've made some progress on this problem in a series of papers that essentially the technical approach, there is some constraint optimization problem that looks both at semantic similarity and let's call it joinability. So I'm going to give an example to kind of give you an idea of where the issues are. So here is the query. What is the highest eligible free rate for K-12 students in schools in the most populous county in California? So the color coding here is the decomposition of the problem. So I go with my semantic search into my collection, and I'm lucky, so I was able to identify the California counties by population. This is a text document, and a table that talks about the free rate for K-12 students. But the problem is that this is sorted by school name. So this table and document do not overlap. I cannot join them. What I need to go further and basically identify another table that links school name to district names, and then district names to county names, and then I can close the loop to the California counties. But these two were not exposed to the queries that I had there. So semantic similarity is not going to help me. So basically another view of this, and starting with the question, I got these two documents through information alignment, basically semantic similarity, but this isn't sufficient. So I have to, in runtime, look at the columns that I have and kind of discern what can be joined with this. And essentially what I'm doing here in runtime, I'm generating a knowledge graph of joinability relations. And this gives me kind of the structural alignment. How to do this? So the way we suggest to do it, so first of all, okay, I would say that standard track isn't sufficient here because it only builds on semantic similarity. And agentic RAG, like React, for example, at least in a simplistic way, is not going to solve it. It's going to get stuck because of the operators that it's using. So what we need to do is, this one approach is that we're looking at a constraint optimization problem that looks at both query object relevance, which is semantic similarity, and object-object compatibility or joinability. And this allows us to kind of dig deeper into the collection, generate this knowledge graph, and this is done multiple times, also in agentic environment, in order to get. So it's a form of enrichment, but sometimes it needs to be done at runtime, given a query rather than in offline, which would be nice. And there's a lot more things that you can do here for exploiting, for example, query log if you have the ability to do it, and many other things. This is really an important problem. And again, closing the loop of the way I started this, vanilla LLM cannot do it. I mean, if you try to solve the same problem with an LLM, basically, give me the query, go to the LLM and ask to generate a SQL query or a Python query or whatever your favorite language is, the results are lousy. The gap between vanilla models and advanced systems, mostly agentic systems today, could be 20 up to 50%. For example, in Spider 2.0, which is one of the academic benchmarks used today, the top results, I said here 61%, I think today it's 65%. If you run it through a vanilla GPT, you're going to get 13%. So these are really, really hard problems and really important problems if we buy into the promise of LLMs or Gen AI that eventually we'll be able to talk to our data. We don't need kind of expert people to write SQL expressions. And one example is a new collection that is called Archer, that is a text-to-SQL challenge with complex arithmetic and reasoning tasks that one of my teams in Oracle played with and participated in this competition. So very happy to say that we won this competition, and we won it with probably 10% above the second system. But look at the absolute results. It's very cool. And this is the case that happens in many, many cases. Whenever we are very impressed, wow, these models are excellent. This Claude code is writing my code and it's solving all the problems. Look at the end-to-end results and you will see that, okay, maybe it's 60%. That's not good enough. I mean, so we still have these gaps that we have to address. So all this is cool and nice. So why is it hard? Again, I'm talking now about kind of this access to data. There are many, many reasons why it's hard. On the database side, schemas have a complex structure. Schema have ambiguous and uninformative names. You can see tables in legacy databases that are called storage 1, storage 2, storage 3. Which one do you want to use? The queries are complex. I mean, I gave you an example of simple queries, but really, sometimes you ask questions that involve multiple information sources. Semantic similarity is still a problem, as I indicated before. And reasoning is hard. We need to aggregate information. We need to deal with temporal references. In many cases, you have counterfactual. I want to know what would have happened had I solved more of this. And hallucination is still a problem. I'm going to give a quick example just to close the loop, because I argued before that hallucination happens. Here's hallucination in the context of an L2C poll. So here is a very simple question. List the area codes in which voters voted for both contestant Tabata Gelling and contestant Kelly Close. The schema is very simple, three tables. So I want to link the contestant name with the area code. And it's very simple. You can see that I can look at the number and link it to this table. And then from this table, I can look at the state, link it to this table, and I'm done. But the model actually hallucinates a path between area code and phone number. It doesn't exist, and I cannot solve it. So hallucination is a real problem, not only when you summarize or answer questions. It's a real problem whenever you do stuff with models. And I'm almost done. There are many other exciting problems to think about, because data comes in many forms. These are all taken from Wikipedia, but you can imagine that the real world have even more. There are many tables, there are charts, there are graphs, and we want to be able to reason about this. So it comes, we all need to deal with multimodal information, temporal information, multilingual information, and it requires not only access, but also aggregation and computation across multiple data objects. So I'm going to address one other buzzword, MCP servers. They're going to save the world. But really, if you think about it, it's also not solving the problem, because MCP servers are excellent abstraction, very useful abstraction, but they're just the connectors. You still need to do the reasoning with respect to the data, and still need to retrieve it rather than relying just on the native retrieval of the tools that you're using. Try to retrieve emails from your whatever client you're using, and you'll see that the native retrievers are actually pretty lousy. Okay, so to summarize, there is an area that I didn't touch, and I think it's really important. In general, from societal perspective, but also for the problems that I already mentioned before. And that is the issue of conflicts, perspectives, and misinformation. So almost all the interesting questions do not have one answer. They have multiple options for answers, and you want to be able to reveal them and say, under this condition, this is the answer, here is evidence. Under those conditions, this is the answer, this is evidence. And we started a line of work in this a few years ago, and we still continue there. I think it's a really important question that kind of relying too much on LLM maybe allows a lot of the community to forget. Conflict is another issue, because all data collections have a lot of conflicts. How do we deal with conflicts? And conflict could arise for many reasons. Sometimes it's spatial conflicts, sometimes it's temporal conflict. Sometimes these are inherent conflicts, and you have to kind of address it, identify it, and deal with it. And of course, there is the mis and disinformation, which is a problem that we have to think about. And I'm going to end with asking you if this video is AI generated or not. What do you think? Why? You say it with confidence?
Well, operated.
Excellent. Wow. First time this happens on the first call. I want to show it again. So you can notice that there's a group of 4 people that eventually, while they are walking, become a group of 3 people. See here a group of 4 people. They will become. So, and this happens because, in the training data, many times there's a group of 4 people that eventually one of them leaves through the door, and there are 3 people. The model just doesn't understand why. So it generates this. So we have some work to do, both in identifying this and doing a better job. So I want to finish here. We conclude. So Clearly, I mean, we're all excited because LLMs can do a lot of good stuff. You know, we are all using it all the time. So there's a lot of merits. But at the same time, it's really important for us to understand limitations. And this is what I call the myth. To understand what doesn't work, why doesn't it work, and what should we do about it. And I can tell you that for me, as someone that kind of wears two hats, just explaining and convincing, you know, business leaders that we haven't solved all the world's problems yet is a challenge because people want to assume that everything is solved. So I try to abstract several lessons, lesson 1, 2, and 3 here. And I didn't get to talk about some problems that I think are really, really important: safety, responsible AI, societal implication of using the models, even when it doesn't make mistakes. And with that, I want to thank many people that contributed to this talk, and thank you.
We have time for maybe a couple of questions.
Yeah, so I'm very curious about the last part of the text to SQL generation. I think you mentioned something about maybe there are some fundamental limitations with agentic systems. So I just want to kind of maybe dig a little bit deeper on that. Can you maybe comment a little bit more on like what do you think are the fundamental difficulties with a model that can actually interact with the environment? So the example, for example, the hallucination example, I think it can be potentially resolved when you have an agent system, because when the model actually call that comment, and then the database can tell you these two keys doesn't connect with each other. So in those cases, because you get feedbacks from the environment, so that's the way you can kind of, even though in the first place that can be hallucination, and then later it can be resolved. So yeah, I'm just curious, like what are some dimensions you are thinking about which cannot be resolved?
Okay, so I hope that everything will be resolved. But I agree with you. So for example, agents that do some verification of what other agents have done would help this and could solve this problem that I've given if they're lucky. Retrieval to me is a fundamental problem because, as I said, when you deal with databases of thousands or tens of thousands, and some of them are legacy tables with ambiguous and uninformative things. Entity linking, for example, is still a problem. I mean, if you go with a query that mentions New York and the tables say NYC, models are not good at it still. So there's a lot of stuff we should do, some offline, some in runtime, with many agents to address. And the difficulty to me is modular retrieval. That is a fundamental problem that hopefully doing better enrichment will solve. There's just a lot of issues. And today, you look at the best agentic systems that we have, say, for Spider 2, there's still a gap of 35%. And it's even a struggle to figure out, okay, so what should I do next? And how do I do it so that I don't solve just this data set problem, but rather something that is general to other data sets. So I'm actually optimistic here. I think we'll be able to make a lot of progress. But I put here kind of the three components that I think are difficult. And I do agree that if we decompose it correctly and employ agents on each one of them with a lot of verification in the way, because they're going to make mistakes on the way, we should be able to make a lot of progress. But it's a hard problem. I think it's going to take time. Yeah.
I had a question about the benchmarks for this problem. I'm curious if the benchmarks take into account like the failure modes when you do make mistakes. Like there are some mistakes that could be a lot more expensive to erase than others. And if there's a correlation between getting more correct answers and making like have higher quality bad answers.
Yeah, it's a good question. So no, the short answer is no. Not only that, today's benchmark don't even take into account the efficiency of the solution. So when you generate, say, SQL, there are many dialects of SQL, and you don't necessarily have to generate SQL. You can generate other language, but you want to generate languages that are formal so that you can actually deal with it. Once you generate these expressions, you then need to go to the database and execute. And depending on the representation you've generated, even if correct, the efficiency of the computation could vary order of magnitude. We don't take this into account, and benchmark don't take this into account today. So there's a lot more to do here to become realistic. Not only size is an issue, and complexity is an issue, but also issues like cost, efficiency, and so on. Yeah.
So you mentioned that today in LLM, they have a lot of things they're not good at yet, right? So we need to add the reasoning part to enhance their capabilities, right? So, but several of the examples you gave, like the agent planning, in a sense, those are new reasoning tasks, right? We don't have old training data to train them, right? So I'm just want to figure out what are the fundamental issues that they're not good at reasoning. Could it be that, with more and more reasoning newer tasks, right? We feed them the data, they will be good at the reasoning tasks that they're not good at today. So yeah. So is there just like somehow with more and more training, more and more examples feed to them, there's still a limit that they can never reach?
So first of all, planning is not a new problem. Planning is an old problem that's was studied, 30, 40 years ago. Scheduling is a planning problem, right? Traveling salesman problem is a planning problem. But older approach were not machine learning based. Machine learning is going to help us to generate approximate solution, but machine learning is not going to solve all instances exactly. Just not possible. These are computationally hard problems. Feed-forward networks, the architecture that we have today cannot solve it. Now, it can solve a lot of the interesting instances, and maybe it's going to be good enough for some domains, but it's not going to solve everything. And when I gave the example of constraint satisfaction, I think that, so my view is that it's a waste of time to try to train the model to solve traveling salesman problem. Instead, I should spend my time training a good translator, because that it will scale also. So then I agree with you. Once we know how to do this reliably, and today we are okay. I mean, we tested until say something like 30 variables. We can translate 80 to 85% correct. I think we can do better, and then we can solve all these class of problems perfectly.
It's just to plug in a logical brain part.
And you need to know when to call it, how to call it, and so on. But I think these parts are more easy to train than to train how to solve the problem.
Yeah. So I'm just asking the when to solve the currently plug-in part, right? Tooling part. Yeah.
Yeah. The tooling is the right approach. We just need to do it better.
You think they can be trained, right? The tooling part.
I'm pretty sure that we can do this better than we do it today. Yeah.
Okay, so let's actually end it here. Professor Roth has to go away.